So the address of alpha would be 1003. Could you encode it? Sure, you got the address, you got the opcodes, why not? Yes.
But what if you were going to jump forward?
What's that?
What if you were going to jump forward?
Yeah, it doesn't work for a very simple reason. You have a loop, and when you're done, you jump out of the loop and you jump forward. That's a forward reference. So if you have this one, and of course I wrote one right on the board here, is this a forward reference?
Yes.
Oh, oops. Forward reference. Does that solve the problem putting the data here? No, it doesn't. Okay, so this one did have a right answer, and I expected everybody to give me the right answer. But yeah, there's a perfect example of why it doesn't work. Okay, so you won't have these questions. These are particular to assemblers. What I was looking for in every case is, does the student understand the issues involved? And please, you do not need to write me the Great American Novel for any of these questions that I ask you. I mean, I'm looking for very specific things, like forward branch out of a loop. So it's what, 5 or 6 words? That was a satisfactory answer. No, won't work. Forward branch out of a loop. Bang. Obvious. That's an example of why it won't work. Okay, C++ code we're not going to do. We are going to do one of these guys. The hand translation to assembler. You remember this one that everybody missed last time? So nobody's going to miss it this time, right? Okay. So I want to make sure everybody's comfortable with the format 3 addressing modes. Format 3 addressing modes. So let's do something simple here as an example. I won't do that one. We can make up one. All right, so on the bottom here, I'm going to have a stored allocation directive. Let's say begin start 0. And then I'm going to say I'm going to need some memory references. So down here on the bottom, I'm saying alpha, word, 10, beta, RESB, easier to add that way. Gamma, word, 20, and then Ada, actually I think it's a different name, data. We got one word for data, and it's too far away from where the program counter is going to be. You with me? So we've got a word alpha, 3 bytes. Beta, 3000 in hex. So this is how many bytes? In decimal.
What?
Anybody? About 12K. So is it going to be out of range? Yes.
Yes.
Okay, so let's get some instructions. L, D, A, alpha, L, D, F. I think it's an LPS and an LPT. It should be like that. Don't want to put down an instruction that does this. Yes, they exist. LDS beta gonna do those instructions. What's that?
Part-time.
Oh, I put the wrong name. That's what I meant. I want to do a format forward. Okay, so we will stop with that. Let's get addresses. Okay, so here. And there's a gap there. We will go ahead and go with it though. So let's get all these addresses. We can do that. So the first one, the LDA is what address?
0.
0. And the next one
3.
should be address 3. And then
6.
6. And then
9.
now the plus, is that 4? Okay, what's this address going to be?
8.
8?
9.
A.
Oh, that's a plus. I thought it was only 2.
Next one is.
The next one is 4 more. I gotcha.
I said 9.
You did, you were right. But I heard some A's out there. I don't know who said them. Okay, so now what's the address of Alpha? 9 and 4.
D.
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 D. I like it. All right, Beta.
1 0.
Yes. And Gamma.
3010.
Okay, and Data.
3070.
Right? Okay. So does everybody agree? I didn't mess up? We got it right? Okay, so I want to encode these instructions now. So we will write the code over here. Okay, LDA alpha. So let's work it out. LDA, the opcode is 0 0. LDA, yes, 0 0. Okay. So we have 0 0. And then I have N, I, X, B, P, and E. And you know what I forgot to put in? I forgot to put in, so we're going to have to fix this. Because we can't do these. Base, gamma. Gamma. My apologies, gamma. And then LDB pound sign gamma, and this one needs a plus. Because it won't work with format 3. So we get to do the address calculations again. That's good. Extra practice. Extra practice. Just think of it. Okay. Now then, let me clean this up a little bit. So what's the address of the LDB? Start. Zero. So this one is, now what's the address of the base gamma? It is says it's 0, but it doesn't occur. I mean, it's removed from, it doesn't form part of the object code. Okay, 0. Now the next one. 4, and then 3, and then next one,
A,
A, and the next one,
E,
D,
E,
E. You want E 14?
B, C, D. No, D, D.
Okay. And now alpha,
1, 1.
1 what?
1.
1, 13 and 4 is 17. That's 17, everybody knows that, right? Okay. And the next one? 1, 4?
Mhm.
And the next one?
3, 0, 1, 4.
And the next one?
3, 0, 1, 7.
Okay. Are we good? Okay. Now then. Plus, let's do the LDB first. It's the first one. LDB. LDB is 68. So 6, 8. Then we have N, I, X, B, E, E. Okay. Is the N bit set? Okay, yes, do it another way. What's the N bit? Indirect. What is indirect? There's an address at that location. Okay. Is there an address at that location? No. There isn't. Okay, so it's not in. What about immediate? Yes, it is immediate. Okay. Now, what about the X bit?
0.
No, you can never have immediate in the X bit. Base relative off the table. Wait a minute, you're loading the base register. Why can't you use the base mode to load the base register? What's that? Well, if it were format 3, would that work? No, you can't use the base register because you haven't loaded it. That's what you're doing right now. Once you're done with this, then you can, but you can't until you do this. Okay, base register's out. PC relative? No. Extended? Yes. Okay, so my digits are 6, 9, 1. 6, 9, 1. And now what? The address of gamma. 6910 30 14. Questions about this? You know, last time on that first test, only maybe a quarter of you got these all right. And like half of you got basically all wrong. So I want to make sure you guys can do this. That's why I'm repeating it on this test. Okay, so I'm going to assume we got this. Next one, LDA alpha. Okay, LDA 00. So the opcode is 00. Now, why are there only 2 zeros here instead of 4? 0, 0, hex digit 0, 0 is the opcode. Why? The format is 6, and the last 2 digits of the opcode are always 0. Okay. N, I, X, B, E, E. Well, base relative mode is now on the table. So we have LDA alpha. Could I encode that using base mode? Yes, of course I can. Sure. Is it valid? Yes. It is a forward reference, but you know where it is. Alpha is at address 1711. Okay, you know where it is. You're ready to go. Could you use base mode? So why not? Because it's a backward reference and base is only forward. Good. Now you may find cases, they're unusual, where both modes are possible, i.e. the memory reference is after your base, which is gamma here, and it's also in range. That can happen. In which case either one works. Okay, but it's not on the table here because we cannot use base mode because it would be a backward reference. Everybody with me? Okay. So it's just LDA alpha, so it's not indirect, not immediate. What am I going to put? 1, 1. And is there an X involved? No. Do you know what that looks like, right? Yes, if it were alpha comma X, then we'd set the X bit. Now what is that addressing? That says, okay, this is load in register A. The contents in memory located at alpha plus whatever's in the X register go to that address. So this is used for indexing, and it's primarily used for arrays. So to get the array index, you put the index in the X register. Okay. Not, yes. Everybody see how we set those? Good. All right. So it's not indirect, not immediate, not X. And then base off the table, be a backwards reference. So it has to be PC relative. No other choice is possible. And then the E bit, of course, is not format 4, so that's always a 0 if it's not format 4. So we now have 0, 3, 2. Okay, what's the rest of it? What's the rest of it? We have 0, 3, 2. How do I figure out what the, well, first of all, let me ask you this. How big is the rest of it? How many digits in hex? 3. 12 bits. Remember, each hex digit is 4 bits, so there's a 12-bit 3 hex digit offset. What's the formula? Destination minus PC. The program counter. All right, we don't have the program counter at assembly time. That's a runtime thing. We do have the address of the location counter. So it's destination minus source plus 3. Yes. What's the destination? It's alpha. It's 11. And what's the source? Well, we're right here. We're right here. LDA is at 4. Plus 3 is 7. And so now what? Isn't 11 minus 7 4? Oh no. Oh dear. 1 minus 7, we can't do it. So we borrow, and we borrow 16. So this becomes 0, we have borrowed 16. We already had 1, so that gives us 17. Minus 7 is 10. A. And then the rest rest of it's all zeros. Everybody see that? So some of you have these really just out to lunch. So I'll expect these to be perfect. Good, good. All right, next one. Next one, LDS beta. Okay, beta's not too far away. So we've got LDS, and that one is 6C. 6C. And then we have NISBDE. Okay, it's not indirect, it's not immediate, just like the last guy. It's not indexed. Base off the table, it's a backward reference, so it must be PC. And E is 0, always before that 3. Okay, so we have 6F2. Now, what's the offset? Again, it's destination minus source plus 3. Okay, where are we going? What are we going to read? The memory reference is beta. And where are we reading it from? 7 plus 3. Yes? Okay, we subtract, and what do we get? 14 minus 10 is 4. No. 20 minus 10 is what? 14 minus 8 is 8, yes. It's 20, 16 plus 4, just in case that caused you to stop a minute. Okay, so we have 6F2. And then the offset is 0, 0. Now how can those both have the same offset? That's got to be an error, right? To get to alpha is A, and to get to beta is A. Somebody tell me why those are both A, but they're going to different places. How can that be? Did we make a mistake? Well, but they're both A. Okay. So it's not a specific location, it's the number of bytes to go forward. In both cases, we're going forward 10 bytes. So if we're 3 back and go 10 forward, and we're 3 back and go 10 forward, that makes sense. So that says go forward 10 bytes. Exactly. Very good. All right. Now, LDT data. Oh dear, there's the troublemaker. LDT data. So the LDT instruction is 7-4. Okay. LDT data. So it's neither indirect nor immediate. So that would be 0, 0, right? No. If it's neither one, it's 1, 1. Why is that? Why didn't they just put zeros there?
Because that's SIC.
Yes, that's backwards compatibility. The SIC architecture only has that addressing mode, so it would be 0, 0, and you would have the full 8-bit opcode in that case. So that is for backward compatibility. An SIC instruction has only one format, the 8-bit opcode and then the 15-bit instruction. And that's a word. It's 24 bits. So here the opcode field is 6 bits. So to distinguish between the two, if it's neither one, and they're both set, that in and of itself is enough to let you know that it's SIC X PC architecture. So it marks the later architecture. X, nope. Okay, well now the assembler isn't going to know that we contrived this example to do a base mode calculation. So there's a general heuristic that you would probably want to follow. Though either way would work. I mean, you could say, if base mode is available, then calculate. Okay, so there are all kinds of things that can go wrong with that. A backward branch. And it would be if we were doing alpha or beta. It would be. So you would calculate alpha and beta using base mode only to discover that it won't work after you did all the work already. So I think a good strategy in general, so you can do that. You can calculate base first to discover it's no good. But I think the best strategy is to always try PC relative first. And if it fails, then go to base mode instead. So let's try PC relative first. All right. So the destination is data. 0, 3, 0, 1, 7, minus source plus 3. Right? You with me? Okay. We subtract, and what do we get? 16 and 7 are 23, minus 13, A. Will that fit in 3 digits? No, it's too big. It's too big. So of course you'd have a check of that to see in your assembler if the displacement is too big. It is. Oops. PC relative is out of business. All right, is base set. And this is a flag. This is an assembler directed base gamma. The set's a flag. It says use gamma. Use gamma as what will be in the base register. So now we don't have the plus 3 thing. We just have destination minus source. Or the base register, but we know what's in it. So where are we going? Data. And what's the source? Gamma. So what is the offset?
3.
It says go forward 3 bytes from gamma. Is this easy? Does that fit in the byte? Of course it does. So we have 770. We good? All right. Now the last one, plus LDA. Okay, because there's a plus, we know it's format 4. LDA starts with 0. And then we have NIXDE. All right, it's neither indirect nor immediate. No X. There's no PC or base relative mode. Neither one. And it is extended. Everybody see that? Okay. So you have 0, 3, 1. Zero, 3, 1. And what's the rest of it?
Isn't the last one supposed to be 774?
Did I get it wrong? What did I do?
You got the one in the B.
Huh? What did I do?
There's a 1 in the B, so you basically.
Yeah.
It's a half bit.
Okay, let's stop. Wait, let's finish this one. And then go back and look at it. If I got it wrong, we need to correct that. You see, I'm allowed to make mistakes, but you guys aren't. Hardly fair, is it? Hardly fair. Okay, so put that on hold. Let's finish this plus LDA data. So what's the rest of it? 03017. It's the actual address. Good? Okay, but let's relook at, take another look at LDT data. See what I did wrong. LDT data. Okay, so the opcode for that, LDT is 74. I see. I think you guys are wrong about that. But let's see. 77. Oh, I have 770. I see what you're telling me. Okay, so we have this, the 77s, right? And the base like that. Okay, I'll buy it. Extra good on the first. Wouldn't that be nice? 774. Are we happy? So it seems like you guys are on top of this. So this is going to go well on the test, I hope. I hope. Yes.
Are we going to have to do any of the linkage on this part?
Not on this, but you will have a linkage exercise similar to the one we did in class last time. So I expect you guys to know how to process that and how to do it. The smart thing to do is make a symbol table. I mean, where you have external symbols. Make sure you know what they are. Okay, some random topics I jotted down here to talk about. See if you guys know all about it. What is a syntax? User-defined symbols. What's a user-defined symbol? A label. And of course, if it's a compiler instead of assembler, that would be things like function names and variables. Here you can have subroutine names that you can create with EQUs, but yes, they're user-defined symbols or tokens in the program. Opcode tab. All the opcodes, just what it sounds like. What's the difference between the location counter and the program counter? Location counter is the address at assembly time. Program counter is the address at runtime. Location counter, of course, is where you're at right now while you're assembling the program. Program counter is where you're at right now when you're running the program. Questions about that? Okay. What's the difference between a compiler and an assembler? Compilers are more complex, yes, but compilers translate higher level languages into machine code, but understand that you can create assembler if you want to out of a compiler. It's an intermediate step. So if you're using C or C++, you can do -s, and it will give you an assembly language file with the output from that program, or that source code. So what makes compilers complex? Yeah, but what does that really mean? If you have something like class person, now how are you going to handle that in machine code? Public class person. Private. Okay, how are you going to do the public and private thing? There are no square bracket or no angle brackets, no square brackets. No brackets, period in the symbol. There's no idea of scope. You either see it in that block of code or you don't. But there's no brackets to define blocks. So there are a lot of things that have to be managed by a compiler, but they have to turn it at some point into this. That's the ultimate goal of a compiler, is to create that. Issues surrounding relocation. What needs to be modified to do relocation? Relocation, of course, means you're going to load this program at any arbitrary place in the computer's memory. And what references do you have that need to be modified or changed? So any memory references you have will have to be changed. Will that need to be changed? If it's a format for it, will. It's the address, right? So, addresses, memory references have to be changed. Do PC and base relative mode encoded instructions have to be changed? No, well, what do you have to do to relocate a format 3 instruction? Nothing. You don't do anything. It doesn't have to be relocated. Why? Because it's a distance within that code program block. I mean, suppose we load this at address 5000. Are these offsets still the same? Is it still going to be 00A? And the answer is yes, because the distance from here to down here is 10 bytes. It doesn't matter where you load it, it's still 10 bytes away. So whatever the address of those instructions are is irrelevant. So what are the issues that surround relocation? Okay, linkage. So we'll have an example of that, linking and loading. Who handles relocation, the linker or the loader? Well, that's the chicken and egg kind of thing. Does the loader handle relocation or does the linker?
The loader is the program memory.
It does, but the linker establishes the pieces and the references between them. And so for relocation, if you're putting a module A, or program A, B, and C, as we did last time, in different places in memory, the references inside of them have to be changed. And it's the linker that does that. The loader, of course, is usually not a separate program. So we talk about linker loaders as a single unit because even though the functionality is quite different, they still have to work together to get the linked program into the right place in memory. Static versus dynamic linking. What does that mean? Static versus dynamic linking.
If it's static, it's the reference is already in the code. If it's dynamic, it makes like a reference to it to a file outside of the code.
Not exactly. Not exactly. There aren't any external references in statically linked programs. There aren't any. So a dynamically linked program will say, okay, this symbol, let's call it sub A. This symbol is at location. So the linker would set that up for dynamic linking, and at runtime, then you would go and grab that. Static linking, there is no reference. It's pulled in and becomes part of the program. So there's, in general, we don't want to do static linking. Problems with it. Now an analogy here. Most of you guys are Java programmers. And Java is a lot more common now than it used to be years ago. It's this big issue that if you've created a commercial program in Java, then you have a jar file that you're going to provide to your customer. But how could you be sure they had a JVM installed in their machine or JRE? How could you be sure they'd have one? Well, you couldn't. You don't. No way you would know for sure that a customer would have the right JRE installed on their computer. So what do? Well, most software would include a copy of the JRE and check and do an install if they didn't have it. All right. Well, in the case of dynamic programs, we have these linked libraries. They're DLLs, DLL files, dynamic linked libraries. And everybody's got them on their computers. They get updated all the time. Microsoft would release a new version. So this does cause problems in some cases. You might have a developer that discovers an undocumented feature in a library. And they write code that relies on this undocumented feature. Then Microsoft releases an update and removes this undocumented feature. They were going to do it, but they never did, but the code was in place, but they've removed it on the update. Now your code doesn't work anymore. So to have problems like that under control, you can do static linking. So with static linking, what does that mean? If you have cout, then the code for cout is pulled into your program and compiled as part of your program. Which means rather than a 10K executable for something like Hello World, you have an enormous one. So I did this once. It's been a few years. I think the compiler's a little better than they used to be, but I basically did a C++ Hello World. It was almost a megabyte in size, the executable. Almost a megabyte. Just to print Hello World. Why? It pulled in all those libraries and compiled them into that standalone executable. They're there. And you don't have to make calls and go find things at runtime. You got it right there. Did you have a question, Kit?
I was just wondering if it's sort of like a macro.
No, what this is all about is you've got all of these external references. I think you see the downside to doing that. How many programs use system out print line? How many Java programs are installed now in Rohan and Eterus that call system out print line? Oh, gee. I hate to think. Well, what about cout? A zillion of them, right? I mean a bunch. So if you have the method for cout and you stick it in 5,000 programs, oh my gosh, you've got 5,000 copies of it, all of these places. Does it really need to be there? Not so much. It's much more efficient to put an address in a program and then at runtime you go and grab it. So that's dynamic linkage versus static. There are times when you're doing something that's probably unholy and you need to be absolutely certain that your program will work correctly. Then you can do a static linkage and a static compile, and then you don't need any runtime libraries. You got nothing to worry about. Never a good idea, but you know, there's this thing called DLL hell. We seem to have that under control now. We're going to have new programs overriding dynamic link libraries and breaking other people's code. Yeah.
So is that kind of like the file parser stage when you import it and copy it from
Right. So those are not dynamically linked because it's a one-of-a-kind thing. But you have things like IOStream, string, all of those libraries. Do you want to pull all of that code into your code and create these enormous executables? Well, it's very wasteful. It is. And in fact, what happens is there are certain regions in memory where most of these libraries are in memory, so it's very fast. You'll even have to hit the disk to pull them in and get it going. But that's the difference. So I want you to understand static versus dynamic linkage. Blocks versus sections. Now these are common English words, but they mean something. And both of these refer to chunks or sections or whatever you want to say. Yeah, code sections, code blocks, right? It's a chunk of code. The question is, where is it? So blocks are within a single .o file. sections are separate .o files. So you can have methods inside the same file. You can do that whether you're doing Java or you're doing C++. You can have functions or methods inside that single file. Or you can have separate files, but the linkage requirements are quite different in those cases. So a block is within the same file, within the same .o file. A section is a separate file, separate .o file. Okay? So in this architecture, he has use and then the name of the section. Use C data. So that's within the same block. The sections, it's C section, but they're named, so they go in separate O files. Xdef, xref. What is xref? This is when you have a memory reference, either to a function or to a label, but you have a memory reference that is used but not defined within the current block. It's used but not declared or defined in the current block. It's an external reference. Macros versus subroutines. What's the difference between the two? If I want to do a swap, can I write it as a macro? Can I write it as a subroutine? Well, what are the pros and cons of the two? Why would I do one and not the other? Yes?
Because macro you can't do recursive.
That's true. Hmm? Macros are inline, i.e. the source code, the body of the function is inserted where that function is called, right in your code. That's the difference. With the function, you have a jump and you jump out to another area of memory where the code is for that function. You execute it and then you return. So if you have 10 calls to the macro in your source code versus 10 subroutine calls, what's going to generate more code? The macros. So what you can see with macros is an enormous expansion of the source code if you're not careful. Macros are best suited to small pieces of code. They're also suitable for code you want to hide from people. Whether it's you want to keep it a secret, you don't usually want to, but you don't want to make them deal with it. You don't want to make them deal with it, so you have a macro call instead. So make sure you know the difference between the two. Which one uses the system stack? Do macros use the system stack? No, they do not. They do not. The system stack is not involved. And this is one reason actually to write macros at the lower levels, because you save stack space for the application programmer if you're not using it. Questions, anybody?
Are we gonna have to expand the macro?
I don't know. You might. It wouldn't surprise me. Yes?
So what chapter should we be reading from
All of the stuff that's been assigned. That is, I'm pulling things from chapter 1 and 2 because you did badly on some of those questions, so they're repeated. So what I would suggest you do is focus on chapters 3 and 4, the linker loaders, the macro preprocessors, and your first exam. The stuff from earlier in the semester I put on this exam only because a shocking number of people messed up on the first exam. Therefore, you should study your first exam questions and then chapters 3 and 4. I'm not including any C++ questions this time. Yes?
Can we ask any validation questions?
I might. I mean, it's not a bad thing to talk about. Suppose the macro only has, the macro definition takes 4 parameters, but the application programmer puts 5. What do you do in that case? Do you just ignore the 5th one? Because when the expansion occurs, what would happen? It just would never be inserted in there. Well, what if I have parameters and I don't use them all? You know, is that an error or is it not? But understand, if I have a reference to a \5 in a macro definition, but I only pass in 3 parameters, then what gets substituted? Well, either a null or an empty string. And then when it gets processed by the assembler, that error will be caught. So this isn't a case where you have to go crazy analyzing things to make sure there are no errors, but the number of parameters should match. The names of the macros should be unique. And it's fairly simple. You don't want to have 2 definitions for a macro. So what you do is, when you get the name of the macro, before you insert it, you look it up and see if it's already there. And if it is, you throw an exception. And if it isn't, you insert it and go on. So it's just a test first to see if it's there. That's how you catch the groups. Other questions? None. Okay. So I hope you guys have a great Thanksgiving. We will come back next week and get an A on this test, and that will set us up to finish the course on a happy